All right, I want to throw everybody totally off today. Everybody write down the word titans. Everybody write down the word titans. Titans. All right, I hope everybody's written down the word titans. Now, the subject of today's lecture is the behavior of different substances in an aqueous environment. Before we can discuss about specific substances, we want to talk real quickly about what has to happen in order for something to conduct electricity. To conduct electricity, a substance has to have charged particles, and those charged particles have to be capable of movement. They can't be fixed in place. There is a category of compounds known as electrolytes, and electrolytes are any substance that when dissolved in water conduct electricity. An electrolyte is any substance that when dissolved in water conducts electricity. You need to write that down if you're not doing so already. All right, so an electrolyte is any substance that when dissolved in water conducts electricity. Well, what's an example of an electrolyte? Once again, I'm going to trot out my favorite go-to example there of sodium chloride. Now, if you just have regular old boring sodium chloride solid and you place a electrical wire in it, you're not going to get any conduction. Why? Because sodium chloride, even though it consists of sodium ions and chloride ions, or charged particles, those charged particles are locked in place in a crystal. We talked about ionic compounds existing in a crystal. Those charged particles inside a crystal can't move. They're being held in place by forces of attraction. And they can't move. Well, when we place them in water, an interesting thing happens. Water is what's known as a polar molecule. Meaning it has a positive end and a negative end. It has a bent shape, so it's kind of like a boomerang here, and our oxygen has a partial negative charge, and the hydrogen tail here has a partial positive charge. Water is so highly polar that these partial negative and partial positive charges are just too attractive for the sodium and the chloride to resist. I mean, let's face it, sodium and chloride, they've been together since the beginning. You know, small town, not a large pool to date, kind of an attraction of convenience. They hit the water, and all of a sudden all these water molecules are running around with partial negative and partial positive charges. How can these ions resist? So when you place sodium chloride in water, the attraction of the sodium ions for the partial negative charge on a water molecule, and the attraction of the chloride ion for the partial positive charge on a water molecule causes the sodium chloride to break up. You place sodium chloride in water, and instead of being that strong crystal, you get a mix of ions now floating around and associating with water molecules. So when you place sodium chloride in water, it breaks up into sodium and into chloride. Now, you have sodium and chloride ions. They're charged particles, correct? They've got a positive charge and negative charge. So now you have charged particles. and they're capable of movement. Instead of being locked in place in this crystal, they're dancing out around among the water molecules. They've entered the great discotheque of life. So when you place an ionic compound in water, it breaks up into ions. Since sodium chloride produces charged particles capable of movement when placed in water, that means sodium chloride is an electrolyte. Sodium chloride is also our representative ionic compound, right? Whenever we need to talk about an ionic compound, I always wind up talking about sodium chloride. Well, all soluble ionic compounds are going to behave exactly like sodium chloride.
N-S-T-I-T-U-E-N-T.
Soluble ionic compounds break up into their constituent ions in water. In other words, when you place sodium and chloride in water, it breaks up into the sodium ion and the chloride ion. You need to be able to write the solubility equation for an ionic compound dissolving in water. All right, write the equation for what happens when sodium sulfate is placed in water. So we have sodium sulfate, and we're placing it in water. What happens? Couple steps are required to do this, and I always recommend that you follow these steps to avoid making simple mistakes. By now you're well versed in your nomenclature rules. So step one, you're going to use your nomenclature rules to identify the ions. You know that this compound is sodium sulfate. That means it's made of two ions, the sodium ion and the sulfate ion. The sodium ion, you know from your periodic table, sodium's in group 1A, so it forms an ion of +1. Sulfate, you've memorized, is SO4 2 negative. Identify the ions. The reason I tell you to identify the ions is people want to make up ions for some reason when they look at this. If you look at it, you've got 2 sodium ions for every 1 sulfate ion, right? For some reason, people want to invent a polyatomic ion. They want to say, I've got that as one of my ions. No, have we ever learned about a binary sodium ion? No, we haven't, right? Don't go inventing ions or inventing new rules. Sodium in an ionic compound exists as a monatomic ion. However, you do have 2 of them. Okay, so step 1, identify your ions. Step 2, write them as products. So I've got sodium, and now it's in water, so it's aqueous. And I have sulfate, and it's in water, so it's aqueous. And notice they are existing as ions now. They've broken up. They're not attracted to each other, so their charge is hanging out there and exposed. So we actually have to write that charge. I didn't just write sodium, I wrote sodium ion. I didn't just write sulfate, I write sulfate with the charge showing. Also, that's an AQ there, right? Phases are going to become very important in this chapter. Phases are almost the point of the entire chapter. So make sure you recognize that these are aqueous. So when I place sodium sulfate in water, it breaks up into sodium and breaks up into sulfate. Now we do have one last thing to do, and that's step 3, to balance. If we look, I have 2 sodiums over here, so I'm going to need 2 sodiums over there. I don't want to invent polyatomic ions, so I'm not going to change my numbers down here. Instead, I'm going to add a coefficient, just like I was balancing a normal chemical equation. Alright, so that's how you write what happens when an ionic compound is placed in water. Let's do one more real quickly. Alright, another example. I strongly recommend pausing me and trying this on your own. Do 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 do. All right. Hopefully you're back from having worked it on your own. We've got magnesium chloride. And I'm dissolving it in water. Notice, I should have pointed out last time, I'm writing my water here above the arrow to show what's happening, but water's not actually participating in the reaction, yes? But to indicate that I've placed my substance in water, I'm writing water right here above the arrow. All right, so step 1, identify those ions. Well, I have magnesium chloride, so one of my ions is going to be magnesium. Magnesium's in group 2A, so it's positive 2. Then I have chloride. Chloride's in group 7A, and it's Cl negative 1. And I think chloride is perhaps the most commonly gotten wrong ion, right? It's Cl negative 1. Even though there's a 2 there, there's no Cl2 2 negative ion, right? That does not exist. Matter of fact, I'm embarrassed I wrote it. I don't want it going into the wrong into your minds there, right? Your ion is Cl negative. We will take care of that subscript on the flip side. All right, so now step 2, I write them as the products. We've got magnesium 2 plus, aqueous, and then we've got the chloride ion, aqueous. Got my charges showing. Now step 3, I do my balancing. I have 1 magnesium here, so I need 1 magnesium here. I have 2 chlorines here, so I need 2 chlorides over there. And that's that. Chemistry's easy, life is hard. All right, let's look at an example of a problem, the type of which, if you have lab, you'll be actually solving in the experimental setting. A 1 molar solution of which of the following would be the best conductor? Well, remember, in order to conduct something, you have to have charged particles capable of movement. The more particles, the better conductor. So, the question really can be thought of as, which of these 3 substances produces the most particles when placed in water? Well, for every 1 mole of potassium nitrate I place in water, I get 2 moles of particles out. For every 1 mole of potassium sulfate I place in water, I get 2 potassium ions and 1 sulfate ion. So for every 1 mole of potassium sulfide I place in water, I wind up with 3 moles of particles. But wait, what about our iron 3 nitrate? For every 1 mole of iron 3 nitrate I place in water, I wind up with 1 iron 3 ion and 3 nitrate ions, or 4 moles of particles. So even though I may have only 1 mole of the starting product, there's a multiplying effect when you place it in water. For every 1 mole of this, I wind up with 4 moles of particles. So even though I'm starting with the same amount of each one of these compounds, the number of particles is radically different, making this a much better conductor at 4 particles per mole than this. And that's the sort of thing you'll be addressing directly in lab. Another common category of electrolytes are acids. Acids can also be electrolytes, but we'll talk more about them later. Let's talk about something that's not an electrolyte. The opposite of an electrolyte is a non-electrolyte. A non-electrolyte is a substance that does not conduct electricities when placed in water. For example, something that gets placed in water quite frequently, ethanol. You take liquid ethanol, you place it in water, and all you get is ethanol that's wet. The water molecules don't pull the atoms of ethanol apart. Notice that we've switched categories of compound. We see carbon and hydrogen there and no metals. Ethanol is a covalent compound. Covalent compounds generally, unless they're an acid or a base, covalent compounds, unless they are an acid or a base, are non-electrolytes. But because they don't come apart in water, they just get wet, and we're not going to spend a lot of time talking about them. Let's move on. All right, now we want to introduce a couple new terms: strong electrolytes and weak electrolytes. Strong electrolytes dissociate completely in water. Weak electrolytes only partially dissociate in water. Let's tackle them one at a time. A strong electrolyte dissociates completely in water. Once again, a great example of a strong electrolyte is table salt. You place table salt in water, if you start with 100 formula units of table salt and you place it in water, then you'll end up with 0 formula units of sodium chloride and 100 sodium ions and 100 chloride ions. In other words, they're Splitsvilles. Their reaction goes to completion. The dissolving of the ionic marriage is complete. There's no going back. The reaction goes to completion for a strong electrolyte. Most ionic compounds are strong electrolytes. So most ionic compounds are strong electrolytes. Another category of strong electrolytes are strong acids. Just a second here. All right. A strong acid. Well, first of all, I don't think we've ever met acids at all. So we should probably pause and define acids. All right, before we define an acid, it's been way too long since we've defined a word for you to write down, just like it's been a really long time since the Browns have anything resembling a franchise quarterback. So why don't you write down the Browns? Write down the Browns. All right, we have to define an acid. An acid is any substance that increases the hydrogen ion content of water. The classic example of an acid is hydrochloric acid. You place hydrochloric acid in water, and just like an ionic compound, it separates into two parts. One of these two parts is a hydrogen ion. Now, the problem is we have a hydrogen ion floating free in water. Well, remember our shape of our water molecule. Our water molecule is bent, but it's a bent shape derived from a tetrahedral. So we have these two hydrogens swept back in one direction, and then we've got two lone pairs of electrons sticking out in the other direction. These two lone pairs of electrons are pure, unadulterated negative charge. And you've got a hydrogen ion, which is a proton, pure, unadulterated positive charge. I got to tell you, these two forces find each other irresistible. So irresistible that in an aqueous solution, this hydrogen ion never actually exists. It is instantly bonded to water, forming a coordinate covalent bond with one of those lone pairs of electrons to form H3O plus, or the hydronium ion. Therefore, you'll often see the definition of an acid somewhat modified. You'll often see the definition of an acid given as, so an acid is anything that increases the hydronium ion content of water. Why? Because you'll never actually see a hydrogen ion floating free. Therefore, how we write acid reactions needs to change to reflect this new definition. All right, so you have an acid, hydrochloric acid. First thing I should point out to you is, how do you know you have an acid? An acid will have hydrogen as the first element. So we see hydrogen there as the first element, so that's a clue we have an acid. Now we place this acid in water. Now instead of just writing that hydrogen ion when the breakup occurs, we're now going to reflect what actually happens in water. And we're going to say it forms the hydronium ion and the chloride ion. And some of you are saying, wait a second, Dr. Kelly. Wait a second. Wait just a minute here. After all, don't we have to have this equation balanced? It looks like we added a bunch of hydrogen and a bunch of oxygen. No, we didn't, right? We have water written above our arrow, It's functioning as a reactant over here. However, it's not something we really want to focus on in our reaction. So even though we're including it in our balance by having hydronium occur over here, we're minimizing its importance by writing it over the arrow, because the main star of our reaction is our acid, as it dissociates to hydronium and chloride. So that's the reason for that unusual notation that you see here. But an acid is anything that increases the hydronium ion content of water. Let's take a look at another example. Another classic example of an acid is nitric acid. Once again, I see my first element is hydrogen, so I have an acid. I place my acid in water, and I wind up with hydronium, and then I wind up with the rest of the acid minus the hydronium ion. Remember, it's a hydrogen ion leaving, which means that whatever is left over is going to develop a negative charge. So you're removing the hydrogen ion. That hydrogen is leaving behind its electron. So we have our nitric acid going to the hydronium ion and going to nitric acid. So that's our acid dissociation reaction. A strong acid is an acid that dissociates completely in water. You're responsible for knowing your strong acids. Your strong acids are perchloric acid, nitric acid, sulfuric acid, then your halogenic acids, hydrochloric, hydrobromic, and hydroiodic. Note, hydrofluoric acid is not on this list. It is not a strong acid. These are your 6 strong acids. You are responsible for this point on now till the end of your existence for knowing that these are your 6 strong acids. All of these acids dissociate completely when placed in water, meaning if I have, let's set up a chart here. Meaning if I start with 100 molecules of nitric acid, then at the end of my reaction, I'm going to have 0 molecules of nitric acid left, 100 hydronium ions, and 100 nitrate ions. And you're probably saying, well, why this big deal? That's the way we've always assumed chemical reactions occur. In reality, a lot of chemical reactions don't occur to completion. Instead, a lot of chemical reactions occur until they reach a state of what is known as equilibrium. Weak acids are examples of such reactions. A weak acid is one that does not dissociate completely in water. An example of a weak acid is hydrofluoric. Hydrofluoric acid when placed in water, does dissociate and form the hydronium ion and the fluoride ion, but only kind of. First of all, notice I've written my arrow a funny looking way. I've got a big arrow, a big half arrow going this direction and a smaller half arrow going that direction. What do we mean when we say hydrofluoric acid doesn't dissociate completely? If I start off with 100 molecules of hydrofluoric acid, at the end of my reaction, I'll have 80 molecules of hydrofluoric acid, 20 hydronium ions, and 20 fluoride ions. In other words, instead of 100% of my molecules breaking up, only 20% will. But wait, there's more. Using the term end is really inappropriate when it comes to a weak acid. Because weak acids are the ultimate drama couple. Everybody went to high school with this couple, right? They're together one moment, they're broken up the next moment. They're together the day before Valentine's Day, they're broken up on Valentine's Day. They're back together the day after Valentine's Day, they're broken up 2 days later, right? Think about any sitcom couple, right? Robin and Ted, Robin and Barney, Ross and Rachel. They're together one moment, they're broken up the next moment. They can't make up their mind. That's how weak acids are. So when we say that our reaction ends, it doesn't really end. It reaches what's known as equilibrium. And at equilibrium, the acids that are the rate of acids breaking up equals the rates of acids reforming. In other words, weak acids reach a state where the number of acid molecules breaking up is equal to the number of acid molecules reforming. So our weak acids we have molecules of weak acids that are constantly breaking up and constantly reforming. In other words, we have a reaction that's a two-way street. Not only that, but they're always occurring. Hydrofluoric acid molecules are always breaking up and new ones are always forming. However, this breakup cycle, this together cycle, eventually reaches a state where the ratio of molecules broken up to molecules together is constant. For example, here we have 20 broken up to 80 together, or a 1/4 ratio. The weak acid will reach a state where that ratio of 1 broken up to every 4 together is constant. The breakups are still occurring and the togethers are still occurring, but the ratio doesn't change. When you reach that state where the ratio is unchanged, that state's referred to as equilibrium. I would say a good 50% of what we will do in 180 deals with this concept of equilibrium. So if you don't understand it fully now, don't sweat it. We're going to spend lots of time on it next semester. Here's the bottom line that you need to get from this one. You need to be comfortable with the fact that for a weak acid, if you start with 100, only some of them are going to break up. And at equilibrium, you'll have 80 together and 20 broken up. So when you have a weak acid, you have less than complete breaking up. A strong acid, you have 100% breaking up. Weak acid, you only have partially broken up things. That gives us two new terms and cycles us back to where we started today. I told you we'd get back there. Speaking of things that always seem to get back there, how is it that the Jaguars always seem to cycle back to the top of the draft? I mean, really, it's the highlight of their season. You'd think they'd be good at it by now, but apparently not. Why don't you write down Jaguars? Write down Jaguars. 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 It occurred to me real quickly, I never told you what your weak acids are. Any acid that is not one of the 6 strong acids is a weak acid. Any acid that is not one of the 6, and that's a 6 there, 6 strong acids is a weak acid. Okay, so a strong electrolyte is an electrolyte that disassociates completely in water. Most soluble ionic compounds and strong acids are strong electrolytes. Weak electrolytes are electrolytes that do not dissociate completely in water. Weak acids are an example of a weak electrolyte. All right. A polyprotic acid. Oh, by the way, this falls under the category of stuff we didn't have anywhere else to place it in the book, so we're slapping it on here. A polyprotic acid is an acid that has more than one acidic hydrogen to lose. The classic example of a polyprotic acid is carbonic acid. Carbonic acid has 2 hydrogens it's capable of losing. The question that you need to ask yourself, and you need to ask yourself as a chemist, is does the carbonic acid molecule lose both hydrogens at once, or does it only lose one at a time? The gut reaction is to say, well, it's got 2 hydrogens that want to leave it, so both are going to leave. Turns out that that is totally wrong. Both hydrogens won't leave the carbonate. Here's why. Let's think about the effects of removing that first hydrogen. We have carbonic acid. We place it in our water. And some of the molecules dissociate to form the hydronium ion and the bicarbonate ion. So we've removed one of our protons. The second proton is going to have to leave the bicarbonate ion if carbonic acid is going to lose both of those protons. We're asking a hydrogen with a positive charge to leave a compound with a negative charge, right? Once that first proton leaves up here, we're left with a bicarbonate ion which has a negative charge. This hydrogen wants to leave with a positive charge. Do you think something with a positive charge wants to leave something with a negative charge? No, it's going to be much harder for it to leave. There are other factors that play into the inability of this hydrogen to leave, but those are subjects for another day. What you need to realize is that when you have a polyprotic acid, such as carbonic acid, if you start off with 100 molecules of carbonic acid, that first reaction will have, at the end of it, 80 of them staying together, 20 of them breaking up. Of the 20 molecules that break up, those 20 bicarbonate ions are the start of another acid reaction. Of those 20 that you start with, maybe 1 will break up, or maybe 2 will break up. So what you see is that even though our carbonic acid has 2 hydrogens to lose, only the first one will be lost to any great extent. A much smaller portion of that second hydrogens will leave the acid. Most of the time, a polyprotic acid is only going to lose 1 hydrogen. Some of the molecules will lose an additional hydrogen, but very, very few, right? We started off our little conversation here with 100 molecules of carbonic acid, and then we wound up with only 2 of them losing both hydrogens, right? So when you have a polyprotic acid, only the first hydrogen leaves to an appreciable degree. Now, there are exceptions to this. Sulfuric acid being a notable exception, where both those one hydrogen leaves completely and the second one leaves in great numbers. But for the most part, only that first hydrogen leaves to an appreciable degree. If you have lab, you'll discuss the ramifications for this for conducting by performing an experiment. In other words, yes, you're listening to this for your pre-lab lecture, but I'm not going to tell you what those ramifications are. What am I kidding you? Let's go ahead and do it. A 0.1 molar solution of which of the following would be a better conductor? Let's deal with a simple one first. Calcium bromide is an ionic compound, and since it's an ionic compound, we know that in the presence of water, it's going to break up. And remember, don't invent polyatomic ions. It's going to form 3 ions, right? It's going to produce 3 particles for every 1 particle of calcium bromide we put in. Our gut reaction is to say, hey, Dr. Kelly, we have carbonic acid up here, so we should get 3 particles out. Bzzz, wrong. That's not what happens. Remember, carbonic acid is a weak acid. So first, it doesn't lose all its hydrogens at once. It only loses 1 at a time. That second hydrogen basically doesn't leave at all. And because it's a weak acid, if I put 100 molecules of this in, only 20 of them may break up. So I only may get 20 charged particles, as opposed to my calcium bromide, where if I put in 100 molecules of it, I get 100 of these and 200 of these. So our conducting solution is going to be much stronger with calcium bromide than our weak acid. And you'll see experimental evidence of it in the laboratory. That's it for this lab. Just like the draft concludes when the Broncos make the last pick. So why doesn't everybody write down Broncos? Broncos. Broncos.